here we have your mean and the target. And that arrow is supposed to actually point at the target with the chalk, I don't know. And the operator, you know, it's kind of like throwing a football. I can make the mark, but I can't do it accurately. Okay, so you have the mean and the standard deviation, right? And you can easily do that. Okay? So now we want to test whether this information is normally distributed. Okay? So what do? We draw the normal curve. That wasn't too bad. Okay? And here is Z, and Z is 0 here, 1 here, 2 here, -1, -2. Okay? Make sense? Okay, well, there's another axis that I'll just kind of draw lightly. It's an x-axis, where x is your x corresponds to your mean and standard deviation. Okay? So, at the middle we have your mean. Okay? So if your mean, if you measure from the left, maybe your mean is 24 centimeters, right? So we put 24 centimeters there, right? If you measure from the right side, maybe it's -32 centimeters, okay? If you measured from the target, maybe it's -0.8 centimeters, right? Okay? So you can choose how that's done depending on what you're getting. Okay? Now, this is your mean plus your standard deviation. Okay? So what do you think this is? Your mean plus 2 times your standard deviation, right? Okay? So, for example, and I'm not going to tell you what this is or this, you can figure that out. Okay? Obviously, your mean minus your standard deviation, your mean minus 2 times your standard deviation. These numbers have to be equally spaced, right? Okay, so now I've got my axis, and I'm going to actually label this a double labeling. I'm going to have Z and X on the axis, right? So Z, of course, is going to be 0, 1, 2, -1, -2, right? And the X might be (17.3), like if you measured from the left side, and your mean is 17.3 centimeters from the left side, right? Okay? And if your standard deviation, now your standard deviations here, if this is the extent of your pattern, your standard deviation would probably be about this. Okay? So if that's 17 centimeters, this is maybe 8 centimeters. Okay? Let's just say your standard deviation is 8 centimeters. Okay? Now, of course, to test your accuracy with this exercise, your standard deviation is the test of your accuracy, right? Now, there's also accuracy and precision, and I'm not going to make that distinction right now. You know, one has to do with how close you average to your target, okay? And the other with just what your standard deviation is, okay? And you kind of combine the two. But let's say, okay, standard deviation 8.0, that's going to make this 25.3 and 33.3, and that's going to make this 11.3 and this 3.3. Get awful close to the edge there, okay? Does that make sense? So when I label this ZX, that means here's the Z's, here's the X's, right? Yes?
Wouldn't it be 9.3 and 1.3?
Okay, 7 minus 9 is, 7 minus 8 is 9, and I don't know what I was thinking. I was talking, you know. I guess I just kind of started, well, I didn't even subtract the same thing both times. So, yeah, I just totally screwed it up. Thank you. Okay? Makes sense? That certainly makes sense that I screwed it up. You see me do that all the time. Okay. Fix the numbers, and now, here's how I'm going to do it. I'm going to say, that's about 0.6 of this. This is about 1/8 of this, right? And we've seen why that's the case. Now we attempt to draw a normal curve, right? And then we ask ourselves, what's the probability that you're between 0 and 1? What percent of your hits ought to be between 17.3 and 25.3, right? Okay? What percent of your hits are between 25.3 and 33.3? You can easily do a trapezoidal approximation to estimate what those percents ought to be. Just based on the numbers that you have. This is 1, this is 0.6, this is 0.135, right? Okay? And you can, you know, you use spreadsheets, you can use a function, and you can refine those calculations as you wish. If you take a statistics course, you'll be given a table that has all those results. Okay? But you don't need the table. Yeah, you probably use one as convenience. But you don't need the table, because you can calculate these things now. Okay? And then what you do is you count how many of these are within 8.3. So let's say your mean is 18.3. You've got 25.3 and 33.3, and you've got 9.3 and 1.3, right? Okay? Now, two things. If you are normally distributed, if your results are normally distributed, and they pretty much should be, okay? If they're normally distributed, then it turns out that this region's about 34% of the total. So is this one. So between here and here is 68%, roughly, okay? And what you got here is about 14%. And what's outside of here is about 2%, okay? And those percents are kind of worth remembering. Those aren't exactly the percents you'll get if you use just the 1, the 0.6, and the 0.135, but they'll be close, okay? And you can easily do, if you do trapezoidal approximation at 1/2, increments of 1/2, so you'd have 4 trapezoids here, you would be as close as those figures, okay? You would get those same figures, I think. Okay, well, you can test that. You can count how many are between here and here. Is that 34% of your total? You can count how many are between here and here. Is that about 14% of your total? Now, if you get, 29% and 19%, yeah, that's pretty close, okay? Because this is the real world and you don't have a great big statistical sample, okay? Now, if you do 100 of them and get precise measurements and are sure that you can distinguish these things, okay, then you get a really good picture of something that has to do with your neural circuitry, okay, between your brain and your hand and everything in between, muscular-neural responses, okay? So it's a very good exercise in experimental psychology, okay? Which goes to things that you don't have any control over, like your neural circuitry, right? You can refine it, and so forth, you'll never get that mean to be the same as your target. Okay? You'll always tend to be right or left. But you might get close. Oh, there are many details there. That's what, incidentally, that's what you would call an experiment in rat psychology. Because a lot of the experiments we do, we don't want to do on people, but rats, in many ways, their muscular neural things are very close to what we measure in human beings. Okay? I mean, you make transformations of your data and stuff like that. And we can, as I say, we can do things to rats that we don't do to people. We still try to be not overtly cruel to them, right? Yeah, we just kill them and dissect their brains and stuff. Okay? And if you wait for a human being to die, you know, the brain's going to be different than it was when you. So you need, then you got to get consent and everything. So we don't do a lot of that, right? Okay? So there, you know, that's good stuff. Okay? There are a lot of things we can do with people. A lot of very carefully designed experiments that rely on this kind of analysis. Okay? So when we do a rat psychology experiment with the class, we're not calling you rats. We're calling you human beings, because this is how we work with human beings as opposed to rats, right? You know, we even have your consent. You can opt out. Okay? You still have to do the analysis.